This lesson deals with design formulas for a full-wave rectified power supply. You can find these notes in the ECE302 ebook in Chapter 2, starting on page 54. In our last video, we looked at a bridge rectifier with a filter capacitor to smooth the output voltage. And we ended the video by calculating the average current in the diode and found that it was related to the average current in the load divided by 2. We can also measure this in the PSpice program with probe, which is the post-processor for graphics, by using this average function. It's defined the following. AVG of y is the running average of y over the range of the x-axis variable. Mathematically, that's 1 over x, the integral from 0 to x of y dt. This becomes our standard definition of average when x is 1 period, from the start of the printed results. It's important to note that you must rerun your simulation, starting with the time when your variable of interest is in steady state. Otherwise, the area during the transient response will also be included in the calculation of average value, and we won't get the right answer. Let's take our PSpice file for the filtered full-wave rectifier. What we need to do is to change where we start collecting data so that we're in steady state. If I were to start my collection of data at half the period, which would be half of 16.666 milli, 8.333 milli, then we could apply this averaging function and probe and get the average value of our current after we change by 1 period, which would be adding 16.666 milliseconds to the 8.333. And that's 25 milliseconds. Here I plotted the average value of I sub D2, and so you get a graph. But when you get to 25 milliseconds, and really every period after that, you get the same value of 8.5789 milliamps. And this is the same value for I sub D4. Do the same thing for I sub D3, and you would get the same value for I sub D1. I get roughly the same number, 8.5790 milli. And then we could say that the sum of those two currents equals the current in the load plus the current in the capacitor on the average. At 25 milliseconds, I get 17.156 milli, which is roughly the sum of those two. And the average capacitor current is a negative nanoamps, which relative to milli looks like 0 amps. We can hand calculate this with our formula, that the average diode current is 1/2 V out over R sub L. If we took 1/2, our average value is 16.95 volts. Dividing that by 1K, I get about 8.4755 milliamps. This is the exact value. Our formulas are an approximation. They get us close, but we can always verify our results. Another thing we need to pick for designing a power supply is the breakdown voltage for the diodes. And when a diode's off, it'll start to conduct if you reach the reverse breakdown voltage. Our circuit on page 47, we saw that the minimum voltage across the diode was minus V sub M plus 1 diode drop. Let's just verify that. Here's the voltage across diode D2, same as D4. And at this particular point, I get minus 19.145. If you add 20 to that, you get the drop across the diode, which is about 0.855 volts. We get the same number for diode D3 and also for diode D1. When we pick a diode, we have to make sure that the reverse breakdown rating is greater in magnitude than this number. Now, most engineers don't like negative numbers, so you'll see data sheets tend to have only positive numbers. It lets you put the signs in. In our particular case here, we're going to take the negative of this result, which would be V sub S maximum minus 1 diode drop. We normally just round it up to the V sub S maximum of the input voltage. In PSpice, there's a way to model this breakdown voltage with 2 parameters. One's called BV and the other one's called IBV. BV is the reverse breakdown voltage, and it's a positive number, and it's defaulted to infinity. Actually, you can take a look at it. If you have a perfect diode, what would happen, and then a non-perfect diode. IBV is the current flowing through the diode at the onset of the reverse breakdown voltage. It too is a positive number, and it's defaulted at 100 picoamps. We can show this pictorially. Here we've got our breakdown voltage, and here we've got the breakdown current. I put minus signs here because these quantities are positive, and they actually occur in this third quadrant. In our last video, on page 47, we saw that there was a one-time surge in current through the diodes due to the slope of V sub S. There's another condition that's even worse. Suppose that at t equals 0, V sub S isn't 0, but actually hits the peak of the sine wave. When you turn a power supply on, you don't know where you are in the sine wave. Suppose that our power supply has been off for a long time, so the voltage across the capacitor is 0, and we flip the switch, and the voltage hits the positive peak. What's going to happen? Well, current's going to want to flow through diodes 2 and 4 and come back to V sub Sm. Let's do Kirchhoff's voltage law. The rise in voltage equals the drop across the diode, but this is at its initial condition of 0, plus the voltage across diode 4. And that would be 2 diode drops. Suppose this was 20 volts. Then using our Shockley equation, we'd have I sub s times e to the v sub d over a to v sub t. Say I sub s is 2 nanoamps. The voltage across the diode, if there's 20 volts, and each diode gets an equal amount of voltage across it because they have the same current through it, and we're assuming that they're identical. Voltage across one diode would be 10 volts divided by eta v sub t. And you get a humongous number. Current would be really approaching infinity. In reality, that doesn't happen because every real voltage source has some source resistance. With 0 volts here, we'd have current flowing through diodes 2 and 4. But now the rise in voltage equals the drop across the resistor, which is the diode current, times R sub s, plus the VD on, plus 0, plus another VD on. The current in the diode is V sub s maximum minus 2 diode drops divided by R sub s. Suppose R sub s were 2 ohms. Then you're looking at about 9.3 amps if we assume a drop of 0.7 across the diode. That's not infinity, but that's still a large number compared to what we had before. This condition, although it doesn't occur all the time, it can occur someday when you flip the switch. You'll get a similar result for minus V sub s maximum where diodes 1 and 3 conduct. If you look back on page 47, we had our input as a floating voltage source. So to build a filtered full rectified power supply, we need a voltage source that's not grounded on either side. And we can do that by using a transformer we talked about in ECE302. Transformers for low power applications pretty much look ideal. Here I've got a primary side and a secondary side, and I'll show my dot notation this way. And a current coming in I'll call the primary current, and the current going out the secondary current. And this is the number of turns on the primary, this is the number of turns on the secondary. If the transformer is ideal, the ratio of the secondary voltage to the primary voltage is equal to the turns ratio of the secondary turns to the primary turns. It's also equal to the ratio of the primary current to the secondary current. In other words, the flipping of the subscripts. The reason that that's there is that if you were to take this and cross multiply, V sub s times I sub s is equal to V sub p times I sub p. And what is that? That's the power in equals the power out. Sometimes we want a dual power supply, so we'll use a center tap transformer. This just takes the previous results and divides it by 2. It gives us a polarity here and a polarity here. If you ground the center, you can get a plus and a minus effect. We'll look at using this in the ECE303 lab to build a power supply. In ECE202, we also talked about a model for a transformer. You can also do the ideal definition, and here's the following. We could use a voltage-controlled voltage source to make the voltage V sub s at the output equal ns over np times V sub p. In other words, you bring this over here. The ratio of the voltages equals the turns ratio. The current I sub p that's coming in here, if we use a current-controlled current source, would then equal to this. I sub p would equal this. So divide by I sub s, and that would be their turns ratio with the p and s flipped. We put together our full-wave rectified power supply that we can plug into the wall outlet. Here we have a transformer. When you purchase a transformer, they usually just list the turns ratio as the number of turns on one side. We'll be stepping down the input voltage, so for every 1 turn here, there are n turns on this side. Let's gather all our formulas and just summarize those. We assumed in picking C sub L that the product of C sub L, R sub L is much, much greater than half a period. The voltage V sub s maximum, which is going to be on the secondary of the transformer, is going to be the input maximum divided by n. And the input's usually given in RMS, so I have to multiply that by the square root of 2 to get the peak value. Our formula for ripple voltage was the difference of V sub s maximum minus 2 diode drops, and then divided by 2f R sub L C sub L. The average value of the voltage at the output is our peak minus half the ripple. The average current is the average voltage divided by R sub L. The average diode current is 1/2 the average output current. We're going to pick our breakdown voltage greater than V sub s maximum. And our surge current is most likely going to be controlled by our series resistance. And that's going to be V sub s maximum minus 2 diode drops divided by R sub s. It's worth noting that some power supplies have an added resistance in series with the secondary in an attempt to increase the total value of R sub s. This will lower the surge to whatever you need for your design. So if you want to design a power supply where you specify V out or specify the ripple, you can work backwards. You'll find examples of this in the supplemental problem sets. And these are the design formulas for a full-wave rectified power supply.